Welcome to This Explainer. Today, we're zooming in on something absolutely massive, the literal ground beneath our feet. But we're not just looking at it like some static postcard. No, we're treating it like a dynamic, constantly shifting crime scene. You can think of modern geomorphologists as the ultimate Earth detectives. These scientists are out there solving the biggest cold cases of our changing planet. They use this incredibly fascinating toolkit to dig up a hidden past, a past full of shifting continents, rising seas, and wild climate swings. And today, we're going to break down exactly how they pull it off.
Okay, let's dive right into this. When Apollo 14 astronaut Edgar Mitchell looked back at Earth from space, he said, "My view of our planet was a glimpse of divinity." And honestly, it is a breathtaking, grand planetary perspective. But what happens when we bring that big picture perspective all the way back down to the dirt? How do we rigorously measure and understand the actual mechanics behind all that divine beauty? Well, to figure out the Earth's history, we basically had to invent an entirely new way of doing ground-level science.
So here's our roadmap for the investigation. First, the geomorphology scientific revolution. Second, dating Earth's hidden past. Third, tracking tectonic plate movements. Fourth, reading ancient shifting shorelines. And finally, number 5, the search for spatial laws.
Chapter 1. The Geomorphology Scientific Revolution.
For a really long time, geography was totally dominated by what's called the Davysian model. This was a classic inductive approach. It was highly descriptive, mostly just concerned with categorizing landforms into historical cycles of development. You went out, you observed a mountain or a valley, you described it, and well, that was pretty much the end of the explanation. But starting around the 1950s, geomorphology underwent this massive revolution. It completely shifted to a deductive approach. The science became process-based, highly quantitative, and leaned heavily into math and exact measurements. We finally stopped just describing static landforms and started rigorously analyzing the actual contemporary processes that create them. This shift is what turned geography into a hardcore, predictive science.
Chapter 2. Dating Earth's Hidden Past.
Now, what's really interesting about this slide is the sheer mathematical rigor we're looking at here. Scientists discovered that stable isotopes of light elements act as literal fingerprints for the past. Let's break that down. If two chemical species, like calcium carbonate and water, reach isotopic equilibrium, the difference in their isotopic ratios is a direct mathematical function of the temperature at which they equilibrated. Meaning, by analyzing the oxygen isotopes trapped inside the microscopic shells of fossilized marine bugs found in deep-sea mud, we can calculate the exact temperature of the oceans millions of years ago. It's wild, we are literally reading the Earth's ancient thermostat.
Chapter 3. Tracking Tectonic Plate Movements. Central to all of this is the field of neotectonics. This is the study of late Cenozoic deformation, which is a fancy way of saying we're assessing the exact rates at which our Earth's crust is moving, both up and down and side to side. Now, this modern field really exploded because of the eventual acceptance of Alfred Wegener's theory of continental drift. For a long time, people mocked Wegener's idea that continents slowly drift over time, but his theory eventually paved the way for the broader plate tectonic paradigm, and that completely revolutionized our understanding of how the Earth works. Suddenly, we realized the ground beneath us wasn't just this fixed, solid rock. It was floating, colliding, and shifting, driven by massive internal forces deep within the Earth.
To kind of anchor all this heavy scientific jargon, let's look at a very tangible historical clue. Over in Pozzuoli, Italy, there are the ruins of the Roman Temple of Serapis. Back in 1847, a scientist named Charles Babbage was examining the columns of this temple, and he noticed something really bizarre. About halfway up, there were these tiny holes bored right into the solid stone by marine mollusks. Since we already know the historical age of these Roman columns, those little holes proved a massive tectonic truth. The land right there had slowly sunk into the sea, long enough for sea critters to literally chew into the rock, and then, later on, the crust was gradually pushed back up above sea level. It is the perfect physical clue left behind by long-term vertical tectonic movement.
Today, the investigative techniques we use to measure these movements are just wildly varied. For the long-term evidence, we can look at things like the physical displacement of the Great Wall of China or the altitude of ancient archaeological remains. But we also use short-term, incredibly precise instrumental tools. We're talking paired gauges on lakes, tilt meters, geodetic leveling, and electronic distance measurement. These tools let us track exactly how the crust is warping and moving under our feet, right in this very moment.
So the crucial point is just how wildly advanced this whole process has become. I mean, we are literally using space technology as a giant tape measure for the Earth's crust. Scientists can actually beam lasers from the Earth onto retroreflectors that were left on the Moon by the Apollo missions. By measuring the exact time it takes for that laser pulse to bounce back, they can track the motion of the Pacific Plate relative to North America. We can measure tectonic plates moving at a rate of 1 single centimeter per year. It is an absolutely stunning feat of Earth detection.
Chapter 4. Reading Ancient Shifting Shorelines.
Whenever we find ancient shorelines that are now stranded miles inland or maybe sitting deep underwater, we're really looking at a tug-of-war between two main forces. One is isosity, which we just talked about. That's the crust itself physically rising or falling. The other force is eustasy. Eustasy refers to the massive transfer of water itself, which directly changes global sea levels. This usually happens because of huge climatic events, like the melting or expanding of massive ice sheets. By studying exactly where these ancient shorelines used to be, scientists can track exactly when and just how severe those global climatic events actually were.
And this brilliantly illustrates how we piece together that shoreline puzzle. Take a look at the height-distance diagram mapping out late glacial shorelines, and then look at the core sample showing lithological sequences. When geomorphologists drill deep down into the Earth, they're reading the layers of sediment like pages in a book. If they pull up a core and find a layer of terrestrial peat sitting right on top of estuary and marine clay, that tells a literal story. It means the sea was regressing, moving away, and allowing land plants to grow right over the old ocean floor. But if they find marine clay layered on top of peat, it means the sea was transgressing or flooding the land. These alternating layers act as a physical barcode of changing sea levels over time.
Let's move to and see how this builds into Chapter 5, The Search for Spatial Laws.
Remember that scientific revolution we talked about back in Chapter 1? Well, it brought a philosophy called positivism straight into geography. Because the whole point of being an Earth detective isn't just to hoard a bunch of data and categorize interesting rocks. The ultimate goal is explanation. It's about finding the empirical, mathematical links between all our observations. Geographers are constantly searching for spatial coincidences so they can establish strict if X then Y laws. By proving exactly how a specific drop in temperature affected global sea levels millions of years ago, or how a tectonic shift totally rerouted a river system, we aren't just looking backward, we are building the exact mathematical models we need to predict the future.
Which leaves us with this final vital thought. We have developed the tools to read the Earth's hidden history, from lunar lasers tracking continental drift all the way to oxygen isotopes mapping out ancient ice ages. The data is clear. And the spatial laws governing our dynamic planet are being written as we speak. So if we can now reliably predict the future based on the deep past, we really have to ask ourselves, based on the rapid environmental changes happening today, what is the Earth telling us happens next? Thank you so much for joining me on this explainer. Keep questioning, keep observing, and I'll catch you next time.